statistical procedures to do inference in science. So it gets over on how do you set things up for science. And there's kind of the idealized world where one approach works one way when you encounter reality. And there's complications in the design and measurement error and missing data, and you really want to fit bigger and bigger models. And it's hard to do the mathematics to do certain things. With Bayesian, sometimes you can do it by constant simulation. See examples of that. Right. So we're going to do a couple more things in chapter 10. The things we're doing with chi-square tests have a big role in something called goodness of fit tests for comparing probability distributions to data. And so it's very flexible and can be used in a lot of different contexts. We had this x squared statistics, Pearson chi-square statistic is what we used in the past. We can use that for this. But we've also looked at likelihood ratio testing. Right? The likelihood under one model or the likelihood of another model, and look at that ratio and getting a sort of test out of it. There's a version of that we can do for discrete data for tables, right? And I call this the x squared statistics for Pearson's chi-squared, and the likelihood ratio, or generalized likelihood ratio, I usually see as g squared. So I'll kind of do that because I think that's what you'll see elsewhere. And then Monday we'll start talking about chapter 11, which is Bayesian statistics. So in this, in goodness of fit testing, let's say we have, a model for, we're going to look at this genetics example as one example where there's a dominant trait and a recessive trait and a certain probability that you get an allele from a parent that is the dominant one, or you get a heterozygous, a dominant one and a recessive, or these two recessives, and it's the probability that you get one A is some probability theta, and probability of little a is 1 minus theta, and you have heterozygous parent and heterozygous parent, each one independently giving one of their genes down here. The probability, well, it's not exactly split because it's not exactly, but that's the idea. But so then the probability of getting two of these is theta squared, and two of these little ones is 1 minus theta squared. And then getting one of each is going to be theta, 1 minus theta, or a little a, big A, so 2 times that, right? So if it's the case that the probability is, say, 0.6, that would imply that 36% here would be that type, 24% over here would be, 0.4 is 16, that's is 0.16. And then in the middle it should be 0.48. Those should be the probabilities of these different outcomes. And so say we have 100 pairs, right? Then it's simple to say we would expect n times these probabilities to occur. We're going to have 100 people. We're going to genetically type them according to this. And so we would expect, in that case, to see 36, 48, and 16. So those are the implications of a model. If we knew that, right? If we knew do this number, right? But let's say we observe, so this is under the model, under truth, say, but let's say we observe 33, right, 52, and 15. And those things add up to our 100 individuals. Well, we don't really know what theta is, so we'll probably estimate it. And what we did with maximum likelihood before is there's 2 contributions of the big A from the first group, there's 1 contribution from the second group, and there's 200 genes in all, and so this ends up being 0.59. Right. And so how many, if this model, if the model is, that says it's theta squared, 2 times theta, 1 minus theta, 1 minus theta squared, right? If this is our model of genetics that we're supposed to be working here, if that's true, how many would we expect in each category? Right? Oops. Right. Get rid of this. And now, so now the expected, based on the maximum likelihood estimate of that portion, is going to be 0.59 squared times 100. Right? And then this one is, well, this one over here, 1 minus that is 0.41 squared times 100. And this one in the middle, there's 2 times 0.59 times 1 minus that is 0.41. That's the probability, and we have 100 of those individuals. So the expected numbers that we get, I'll write it in red to make it stand out, 34.81, and 16.81 for this one, and 48.38. And there's no particular reason I wrote them up or down, I'm just trying to fit it in. So those would be the expected under the model hypothesis with the parameters stuck at the MLE. Right? And so then the question is, does this model look reasonable if we put the MLE, the unknown parameter at the MLE? Right? And so we can use our chi-square testing, our chi-square statistic, to compare the observed ones to these that are estimated under the model. Right? And in our expected, with the MLE put in there, it's a little different from truth, expected value. It's actually a little bit closer. Well, is it a little bit closer? No, it's a little further away. For this one, I guess this one is probably, this is a little bit closer. Right? And that one's a little, so they're kind of can be a little bit closer to our data, depending on how that goes. Right? So for testing, we have a hypothesis, right? So the null hypothesis is going to be this particular genetic model that we like. Right? And the alternative is that this model is incorrect. This model does not fit. Our data, this is a fit testing. Erasers. Okay. And so we're going to calculate this x squared statistic where we sum over all of our categories. Sometime before we called this cells when it was a 2, but it's generically just all the different categories we have of the observed minus the expected squared over the expected. So in this case, we had 33 minus 34.81 squared over 34.81. And the next one was 52 minus the 48.38 squared over the 48.38. And the last one, the third category, is 15 minus our 16.81 squared over the 16.81. We calculate that out, the chi-squared value. Do I have that number here? I think it's 2.48. No, it's not. It's 1.1. There it is. I'm looking for it in my notes. So that's the discrepancy. So even though that's almost a discrepancy of 2, right? Well, 2 squared would be 4, but 4 over 16 is about a quarter. So these things don't add very much in it. So there's a discrepancy of 4, so that squared is 16, and 16 over that is about a third. So it doesn't add up to all that much. And so the question is that large? We're going to compare our statistic, x squared, to a certain chi-square distribution. And the question is what degrees of freedom to use. For things like this, there's 3 cells, right? But they do have to add up to n. Proportions have to add up to 1. So you lose 1 there. Right? There's not 3 independent things. There's maybe 2 independent things. But we had to estimate 1 parameter. Right? So we had to estimate the proportion. So we subtract 1 more. So we use a chi-square 1 on this. Right? And the 95th percentile of a chi-square 1 is the 3.84. Right? And so this number is not past that. Right? The chi-square 1 kind of looked like this. Right? And so our x-squared statistic should have that distribution. Our critical value for rejecting the null hypothesis is we got to be out here past 3.84. Where are we? We have our actual value of 1.13 for this table. So if the model's correct, we're not out in the extremes, we don't reject. So it looked like if these data that we have, maybe this genetic model is correct, maybe it's reasonable. The goodness of fit says we can't reject it. It doesn't seem inconsistent with that. Right?
Why do we lose a degree of freedom for estimating the parameter?
Well, so between the two, it's really the difference in the number of free parameters between this. Right? And so in the genetic, when there is no model, you just have three proportions that have to add up. You could say that there's two free parameters. Right? Whereas in this, there's only theta. Right? So there's one. So the difference in the number of parameters is one. So one way of counting that is there's 3 cells. You lose 1 because everything has to add up to the n, or the proportions have to add up to 1. So there's 1 less. And you have this extra parameter for evaluating it. Sometimes it can be a little tricky trying to count the degrees of freedom in more complex models and situations. Right? Oh, yes.
Can you just go back for a quick second? How did you get the 0.59 again? You times 2 times 33.
Yeah, so that was... So based on these data, right, based on these numbers,
yes.
right, this would be the maximum likelihood estimate of theta. We looked at some genetic examples like this before. So there's 100 individuals, really 200 genes, and if all the alleles coming in there are independent, it's like 200 independent observations.
Yes.
And in the AA one, we get 2 large A's. And here we get 1 large A.
Okay.
And so it did come from the likelihood.
Okay.
Right? Theta squared raised to the 33rd power, 2 times theta, 1 minus theta raised to the 52nd power, and then that 1 minus theta raised to the 15th. And we maximize that and end up getting that value. So it ended up being a little bit different. What if the data were a little bit different? Right? Under here. So let's say instead of that, we had some different data. Right? And so the AA version, if that had been 31 and 56 and 13, right, this still leads to theta hat being 0.59. Things have been adjusted, like 2 have been taken away from there, and 4 have been added to here, so it ends up being the same estimator of the proportion, right? Same MLE. Right? So we're going to have the same expected values as before, right? 34.81, 48.38, and 16.81. Now we've pulled away a little bit. Right? So if those are our data, chi-square statistic ends up being 2.48. Again, degrees of freedom is 1, like we discussed. So the cutoff point that we have to get beyond is the 3.84. And so we still do not reject that genetic model. Right? We're not it's not doing as good of a job of explaining the data. The data are a little bit further away, but it's not yet statistically really kind of unusual. Right? So same expected values because the model is still the same and that unknown parameter happens to have the same. So let's do one more change, right, to the data. Version number 3, if the data that we see had been 29, so that's decreasing to, I'm going to increase this one to 60, and this has to be 11. Again, I set it up to get the same parameter estimate, so same expected values. Now I'm going to compare these. So we've pulled further away from what the model says. Right? Getting the MLE under the model is kind of the best choice of that parameter for these data. But that doesn't mean it's necessarily very good. Right? That the model still might be wrong, even though we've done the best we can for the parameter. In this case, the chi-square statistic is 5.77. And if we compare that to 3.84, we're out there further. Right? So the first table is not much different at all. And then we moved a little bit further away, and the statistic got bigger. And if we move further away from what the model would say under the expected values, the statistic gets bigger, and in this case, we would reject. So there's some, appears to be reject H0, reject the use of this genetic model. Something else is going on here. The middle category is just a lot more common than this independent association would happen. So maybe, I don't know. I don't have a good biological explanation for why that would happen, why you'd get more heterogeneous individuals than homozygous. Maybe there's something undesirable about being homozygous in the population, and so a mix gives you some advantage. Some genetic conditions are actually like that, right? So, what is
Sickle
it?
cell anemia.
Sickle cell anemia is that way, right? So the data would. So this is an example of goodness of fit testing. Right? We could use right. The other way that it gets used, we aren't going to review a number of things. Well, you look at like an example, right? So, another application that you look at with an example that you will on the homework, right? Post it, right? Is that the data come from Poisson distribution. Right? And so this implies that the probability that you see some number of observations is lambda to the x e to the negative lambda over x factorial. You can get the probability. So if you have n observations, we expect the value x. I'm going to call this just a little piece of x for the probability we get x of them. Expect value x to occur, right, on average, n times piece of x times. So if we knew lambda, you could tell me how many times out of, say, 100 observations you would expect to see 0, or 1, or 2, or something like that. And so we estimate lambda. Our lambda hat, our MLE, just for Poisson, it just turns out to be just the average count out of n observations. Then we can calculate the expected value that we see, and we can compare it to our own tabulation. How many zeros, ones, twos, and other things do we have? And the alternative is that, that our data do not come from a single Poisson random variable. There are many ways that a single Poisson random variable can fail to fit a series of counts. They could have extra zeros, like doesn't apply to a bunch of cases, so you get an extra load of zeros in there and it doesn't fit the Poisson model. Sometimes you take samples and it's really a mix of two populations, so it's maybe more variable than one Poisson. And so you just can get a number of different things. Right? Sometimes a Poisson implies too large of a tail, and so it's really kind of truncated. It doesn't go up that high. So there's a number of ways that it can fail. Right? But under the Poisson model, we have the probabilities. We can estimate that and then compare the observed counts, the number of zeros, ones, twos, and so on, to what would be predicted. So any number of different models, continuous models, sometimes you divide the intervals up and say what percent should fall in different categories, different ranges, how many do you actually see, but the model has a mean and variance. So you estimate those. So you can do a lot of different comparisons there. And we just kind of scratch the surface by illustrating, one or two. Right? So our chi-square gets used for that, right? But the second topic is going to be that this testing is also done with likelihood ratios. But before we go on to that, any other questions on this genetics example or what we're doing? I will post a homework and have a problem that we do a little bit of this, and there's some directions kind of dealing with the Poisson. A couple little wrinkles in dealing with some of these distributions, but once you do that, it follows the same logic. We have a model that says we have a certain distribution, we estimate the parameters we don't know, find expected values, and then do a comparison. Okay, so for the likelihood ratio, we are going to think about 2x2 tables to do this, or dimensional tables. You can think about cross classifications, two-way tables. A null hypothesis that says that the dimensions are independent of one another. Independent row and column variables. Can be written as the probability of being in a certain row ij. These can be more. These don't just have to be two. They can be multiple rows and multiple columns. The probability that you're in row I, column j. Right, so here's an I, right, and here's a j, right, and here's my ij spot that's in there, is the probability you're in the ith row, right, times the probability you're in the jth column. I also wrote this sometimes as, put an R subscript for the row and a J subscript for the column. There's different ways people present this, but it's multiplicative. The chance that you're in simultaneously a certain row and column is the product of the two probabilities because of the independence. Right? And so the alternative is not independent. And the likelihood that we have for a multinomial, right, this is something called multinomial, the PIJs, is essentially the probabilities raised to the power of the number of times it happens. Right? So if xij, I going 1 up to I, and j going 1 up to big J, are the counts observed in cells ij, right? And p sub ij are the probabilities. Right? The probability we see, all of our table of counts, that we see that one under a model. So this is our xij's, the whole combination of them, the whole set of them. Under this model is there's a combinatorial term out here, but it's basically a product over the i's and a product over the j's of the pij's raised to the xij's. This is similar to binomials where we have p to the x, 1 minus p to the n minus x. Right? Or the genetic one where we take the theta squared raised to the count, the middle probability raised to its count, or the 1 minus theta squared raised to its count. The same general thing happens with bigger tables probabilities. So this could be viewed as the likelihood for all these PIJs, all these several parameters. So guess what? We're going to find the maximum likelihood estimates of the proportions under the independence model and the maximum likelihood estimates of the proportions under the general model that says there is no specific relationship. Right? So find MLEs. under H0 and under the alternative. So P under the HA, that says there is no particular relationship. The Pij hat is just going to be the count in that cell divided by the proportion. So everyone just kind of stands for themselves. Under this one, we're going to estimate the row 1 and we're going to estimate the column 1, right, separately and just multiply them together. And so the likelihood ratio test would say take the ratio, right, take a product over all the different cells in our table of the model, the likelihood using those, divided by the likelihood using those. And so we put this in the numerator, and we put this in the denominator. That's raised to the xij, right, because that's how many times we're in I by j. This is a P, not an R. In the denominator, it's the Pij hat raised to that power. So we can kind of put those things together. And so we're going to reject the simpler model that says independence if this thing is small. Right. If the likelihood ratio is pretty small, we're going to reject that and say it's not good, right? But figuring out the exact combinatorics in a big table is kind of computationally, messy. So the generalized likelihood ratio test statistics, we take -2 the log of this, right? And we compare that to a certain chi-square distribution. Right? And what happens if you take -2 the log of this? Well, you can get -2. The log of a product can go the sum of a log, sum over all the cells ij. The log of the thing inside, you can put xij out here, and then the log of pi hat r, the ratio of these probabilities, pj hat column over pij hat. Right. So you can take this ratio for each cell, take the log of it, multiply it by the number of times that happens, add them up, and the -2 is there. And so that's the basic statistic. With the negatives, we can actually flip these over top. And this thing was xij over n. Right? And so if we multiply by n, we'd get xij back. Right? This is the probability under that model. Right? If we multiply that by n, we get the expected value under independence. So an equivalent way of writing this thing, right, this g squared, this generalized likelihood ratio test statistic, is 2 times the sum of the xij's and the log of the xij's over the expected values. So observed is the xij's, and this is the expected under independence. And so that thing should have a chi-square distribution in reasonably large samples. You don't want any of the x's to be z. Well, some of the x's could be 0, right? You could have some zeros as long as the expected value is not 0. And the way you treat that is, if it's 0, you're multiplying by 0. So even 0, log of 0 is negative infinity. Just the zeros, you just kind of don't add it in. Right? And so we can do our testing like this. Right? So let's say we had, and so this becomes an alternative test statistic to the Pearson x squared. Right? So let's look at an example. Maybe I'll just put it on another page so we can do it all in one. Let's say we have a medical example where we have a treatment, right, and then a control group. And we have 80 that get treatment and 90 that are getting control. And we have a positive or a negative outcome for the different individuals. Right? And let's say of the 80, we get 24 positives and 56 negatives. And for these 90, we get 19 and 71. Right? Is there a difference between the rate of treatment and control in terms of getting better? One way of doing this is just doing a two-sample test and saying, is the proportion getting better? Treatment, control, right? So we could look at the proportion getting better among the treatment. It's 24 over 80. That's 0.30. And the proportion getting better under the control is 19 over 90. And it's 0.21. Right, so there's a 9% difference there, but these are kind of small sample sizes, right? So you might do a two-sample test of proportions, but you could also use chi-square tests, right? So null hypothesis that would say that the two proportions are the same of getting better is equivalent to saying that these two things are independent, right? And so that the chance you're in one of these four cells, the four cells there is the chance you're in a certain row times the chance you're in a certain column. And to get expected values, undo that null hypothesis, right? We start with our 80 and 90, right? And then we find how many are in each column. So that's 43, there's 170 in all, and that adds up to 87. Have I done? No, that's one. I misread my number there. So it's 7. It's 120. So that adds up to that, right? So we get those margins, and so, for instance, the expected value over there, we would take the 43 times 80 over 170, right? And that'll give us how many we would expect there under independence. That's 20.24. So 20.24. If you do a similar thing for the other three, and once you do one in a 2x2 table, they have to add up. So, but it's 59.76, and this one adds up, so 22.76, and this way 67.24. What are the expected values? And then we can compute either the x squared or the g squared statistics. Right? X squared is 1.771. I wouldn't necessarily always keep so many decimals, but g squared is 1.770. They end up being quite close in this case. There can be a discrepancy. There's always a slight discrepancy. In this case, they don't end up being too different. Right? Are these large values? Are these values large enough to say that these things are not independent? Right? And is chi-square with 1 degree of freedom? Right. So the 0.95 cutoff is, again, 3.84. And so we do not reject the null hypothesis. Meaning that we haven't really proven that conclusively that there's a benefit to treatment in this small sample. Things are optimistic, it's 9% better, but it's small sample sizes. So it doesn't really convince us that it's not just random. It could be an encouraging pilot study, right? But it's not going to be kind of the final proof. And either statistic gives this, right? Why are those quite so similar? All these expected values were pretty decent size, right? if you had one of these expected values that was much smaller, like closer to 5 or something like that, then the g squared, x squared tend to pull apart a little bit more because they handle a small divisor, a small expected value in the divisor or in the log, it magnifies the difference a little bit. But once they're bigger, it's not too much difference. But they're developed independently by different people, and can both be used. But any questions about it?
So why would you use?
Why would you use one or the other? It's not going to make all that much difference in that, realistically. It's a thing where generally the three methods, the two sample test of proportions, just comparing those directly, or the x squared or the g squared, in most cases will give the same result, right? And they could slightly differ, but it's kind of interesting that they've come from different perspectives a little bit. The generalized likelihood ratio fits in with maximum likelihood and Fisher information, and using the probability structure of the data more directly. Right. So sometimes you'll see one or the other. I'm just trying to think of, there's some other things, other model comparison things that get used in regression or in larger models that are more based on the likelihood. So as things get bigger and more complex, things tend to drift towards things based on the likelihood, right? Because that kind of gives you a little bit more structure to work with instead of trying to be creative and think of things out of the blue. Write down the likelihood, deal with the likelihood, and find tests and confidence intervals and procedures out of that. So this is a 2x2. It's perfectly fine to use either of these statistics also for goodness of fit testing. Right? What are our degrees of freedom here? I've said degrees of freedom 1. Right? We had 4 cells here. Right? How did we end up with 1? We had 4. Right? Everything has to add up to 1. Right? All the proportions across all 4 cells add up to 1. Or the counts add up to n, or it's fixed sample size, right? And how many parameters do we have to estimate? Right? Row proportion, column proportion, and then 1 minus is the other one. So we had to estimate 2. So that's why we're at 1, right? The first hypothesis, you estimate 2 things, right? The null hypothesis, you have to estimate the row proportion and the column proportion for success or whatever. And then the alternative, you have to estimate 3 proportions. Add up. So there's a difference of 1 there. So, okay. So one more example. We've looked at M&Ms before, right? But why not? Right? We'll use this, and we get another fun application on Monday with Bayesian statistics. In 1997, there was brown, yellow. These were I could almost use the colors up here for this, right? Orange, that's you, orange, green, and blue. Right? The proportions of M&Ms produced and put randomly into the sacks apparently were 0.30, 0.20, 0.20, 0.10, 0.10. That's apparently what it was in 1977. In 2008, the proportions were changed, 0.13, 0.14, 0.13, 0.20, 0.16, 0.24. Apparently, in 2017, in a factory that made these in 2016. Oops. These, there was proportions of 0.135, 0.145. So I don't know. It's getting a little bit more detailed. Oh no. This is. I'm sorry. I should write better notes to myself. Right? So in sorry about that. Get this figured out. 2017 in a factory in New Jersey, they made them 125, 125, 125, 25% orange, 125, and 25% blue. And then in 2017, in a factory in Tennessee, an article said they made them 124, 0.135, 0.131, 0.205, 0.198, and 0.207. Right? So every single line of this, right, is a model that says this is the distribution that these things have. Right? And somebody gathered some data. And so the data were gathered in 2016. And they had as counts 96 of browns, 103 of yellows, 108, 133, 139, and 133. So these were the data. And in all there was 712 different observations. And so a question could be is which of these, were any of these models plausible origins for the data that they had for the different M&Ms, right? And so we could use testing, right? So
Would we calculate the expected?
under one of these different models, right? So if we did that, so we could do kind of one of these, for instance. I do have the M&M, so you can take some to go if you want, or you can take yours and try and think about does it apply? And we'll get another fun example on Monday. So if the proportions, right, are like the first 0.30. I guess you can't see both. But and then the yellow was 0.2, and then red was 0.2 and 0.1, 0.1 and 0.1 for those. Good to see if the proportions, oh, I typed it doesn't, up there I found an error, that's 0.1. So the sum is 1, so that looks good. And so we would expect is 712 times the proportions. So we'd expect that number if 1977 ones. What's the observed values? I said it was 96, 103, 108, 133, 139, and 133. So E is this, O is that. You kind of have to do some mapping over there. It might be hard for you to see anyway. But it doesn't look very close, right? It doesn't look like the 1977 factory made these M&Ms. And if they ate in 2016, that's probably good. Right? So we can calculate our x squared statistic, right? The sum of observed minus expected squared over expected, 255. Right? And the other one is 2 times the sum of the logs. Right? There's observed times the log of observed over expected. Right? So that's 238. So there's a little bit of difference there. They're still big numbers. How many degrees of freedom is this test? Right. So how many M&M categories? There's 1, 2, 3, 4, 5, 6 categories for M&Ms.
Minus.
Essentially, 1, because everything has to add up. And then
5.
yeah, that'd be 5, but we subtract 1 more, right, in there. So what would be the rationale for that? We have 6 categories, they have to add up to 1. And, well, so under the first one, we estimate no parameters, but they have to add up to 1. So there's kind of 5 independent deviations. And in the next one, we have to estimate all of them. So really, we're estimating 5 things. So I believe that the number we would use is 4. Right? the chi-square with 4 degrees, the 0.95 place for 4 degrees of freedom is 9.449. And we're clearly beyond that, right? So that would conclude that this category, this one up here, is totally inconsistent with the data that we have. And we could test any one of these two, right, to see if it would fit better. So I could calculate, put those proportions, change the expected values, and what you get for these statistics. So there's if the null hypothesis, right, is 1997, we get an x squared value that's 255.8. The g squared value is 238.4. A small difference in, I don't know. Anyway, it's still a large number. The 2008 one, you think that's going to be a smaller number or a bigger number? Right, so these proportions, right, if you do that, this is 0.135, right, 0.145, 0.151. This one is 0.187, 0.195, and 0.187.
Just gonna be small.
It's a little bit more equal, right? And so in comparison to this 2008 one, it's kind of noticeably closer, right, to what the model said. So we'd expect the statistics all to be, close, smaller. This is, right, 17.35 and 17.57. Closer, but we'd still reject it. It does not look like it fits the data. Where was it particularly kind of bad? If we go back, right, it's a lot less here, right? There's more there. That's not too bad. That's not too bad. It's kind of, in these two, they seem to be kind of off particularly at the end. So probably that's the biggest. You could calculate O minus E over the square root of E, kind of get the contribution to that statistic to see where it's worse. How about these next two?
It's probably like the Tennessee one.
Yeah, it really is kind of looking pretty close to that, isn't it?
Yeah.
And this one, is looking better maybe. Well, it kind of has some problems between those. You can see where it's kind of different. So, get back to this. And so the New Jersey one, 2017, this had 57 points. So this one's actually worse, 6 something, and 55.33. We're going to reject that one. But the Tennessee one looks like the winner. 6.07, 6.01. It's not perfect, but our chi-square for the 0.95 had 9.49 as the cutoff, and so we do not reject. Right? So if you had to bet, you'd probably say that it looks like they're made. These were samples from a production in that area or something similar. And so you can do a lot of varieties of testing for that, and it comes from a different, Anyway. But that's kind of what we're going to do. We've done different ways of looking at one proportion or two proportions. We thought about simulation of these. There's a couple big sample tests for two-way tables, the Pearson's chi-square or this likelihood ratio test, which gets applied to a whole variety of scenarios, and we can do testing. Right? So, do you want to see where these are made? Do you want one? To see, I didn't look up the data we had before, that everybody can have. No, you don't want it. Anybody wants out?
Thank you.
There you go. Oh, here you go. Yes. Yes, there you go. Can I talk on you? Oh, there we made it. Oh, sorry. You can either gather the data, or you can remember what we had before.
Is this your leftover Halloween candy?
Something like that, yeah. We don't get that many trick-or-treaters. So I don't know, if we wanted to count them up, we could, or just kind of a method. You want to test it out?
I was gonna save mine.
You're gonna save yours, yeah.
Other people can test that.
Or you can- But anyway, that'd be the idea. With one sample, it could be from any of these, right? One sample isn't gonna be big enough to test much of anything. But, you know, you kind of get you see a small sample, you kind of get your inclination that things are so imbalanced. You get a lot of these. I don't remember where it was in the past that we've done that, so. But anyway, that's kind of what we'll do. You can save the rest to that, think about what it would be. And we've not reflecting the homework, so we have the homework that's here. On Monday, we'll start talking about Bayesian. We'll start looking at a different way of doing testing and inference. So.
It's strange that the proportions are so skewed. Wouldn't you think it would be even?
Yeah, you know, I don't know if they go on popularity or they go on cost, right?
Popularity? Who's gonna say I prefer one color over the other? The same
Also colors.
It's brought 100% out of the car, but it's sentimental.
What do you guys think cost?
Yeah.
Yes.
No, it's all center, makes it do you want to come in and talk about it? Brown.
Yes.
Thank you.
Yes, that, if I don't have copies here,
Oh, they all copies.
but it's on the syllabus, and there's a
Yeah, I
link
saw
on
it on the
the,
syllabus, I just didn't remember getting the project itself.
yeah,
And where you meant it.
yep.
Alright,
It should be listed on the website for the class.
alright, yeah.
So then, you run your assignment,
Yeah.
and down there a little bit.
Alright,
Right, so under the projects and presentation, there's a.
Yeah.
All right, thank you. Sure. Thanks. Yep.
Thank you.
Thank you.